Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Acid-catalyzed hydrolysis of a cyclic acetyl, 1,3-dioxylane, releases the parent carbonyl compound and the diol. However, in this case the acetyl is not a simple 1,3-dioxylane derived from an aldehyde or ketone with ethylene glycol. Instead, it is a cyclic formyl, methylene acetyl, where the OCH2O bridges to adjacent oxygen atoms on the aromatic ring. Moving on to the next step. Identify the substrate. The starting material is a compound where the benzene ring bears a free OH at the para position, C4, and at the ortho positions, C1 and C2, the two oxygens are bridged by a CH2 group forming a 5-membered cyclic acetyl, OCH2O. This is a cyclic formyl, methylene acetyl, of catechol, with an additional para, i.e., it is the methylene acetyl of 3,4-dihydroxyphenol, hydroxycatechol pyrogallol derivative, specifically the 3,4-methylenedeoxyphenol with OH at C1. Moving on to the next step. Acid hydrolysis of the cyclic acetyl. Under H3O+ conditions, the CO bonds of the acetyl are cleaved. The OCH2O group hydrolyzes, the CH2 bridging two oxygens is released as formaldehyde, HCHO, and the two oxygens revert to free OH groups. And for the final step, the two oxygens that were part of the acetyl ring become free OH groups on the ring, C1 and C2 positions, and the para at C4 remains. This gives 1,2,4-trihydroxybenzene, also called hydroxyhydroquinone or 1,2,4-benzenetriol, which matches option A. The CH2 of the OCH2O is released as formaldehyde, HCHO, which matches option C. Why not B? Option B shows a non-aromatic, cyclohexane type, triol, which would require reduction of the ring. This does not occur under simple acid hydrolysis conditions. Acid hydrolysis of an acetyl does not reduce the aromatic ring. Both A and C are produced simultaneously in the same hydrolysis reaction. Therefore, option D is correct. Therefore, the correct answer is D. Therefore, the correct answer is option D.